Have you ever stopped, just for a moment, and wondered why the universe seems to invite our curiosity so quietly, yet so insistently, as if it knows we cannot resist asking where we come from and what, exactly? All of this is for, well, you see, from the time we first looked up at the night sky and traced patterns between distant points of light, something stirred inside us. A sense that the universe is not merely out there, cold and unreachable, but somehow connected to us, breathing through the same laws that shape our memories, our bodies, our fleeting lives. Perhaps you have felt it too. That strange mixture of smallness and belonging when you gaze at the stars and realize they are ancient, unimaginably old, yet their light is only reaching your eyes now. And that's the thing. The universe is not just a backdrop to our existence. It shapes time itself. It governs the atoms in your bones and the thoughts forming in your mind right now. Many people imagine the universe as empty space sprinkled with stars, distant and irrelevant to everyday life. But modern science, slowly and humbly, has shown us something far more intimate. Space stretches. Time bends. Gravity whispers across billions of years. And in understanding these ideas, we begin to see ourselves differently. I suppose that is why we keep asking questions. Why did it begin? Does it have an edge? Is it expanding into something or nothing? And what does it mean that we are here, conscious, asking these questions at all? This journey is not about memorizing facts. It is about pausing, listening, and allowing wonder back into our lives. As we explore these truths together, you may find that the universe feels less like a mystery to be solved and more like a story we are part of, one chapter among many, written in starlight and time. Before we go on, I'd like to ask you to subscribe to the channel and leave a like. My aim here is simple, to help you drift off to sleep while exploring the wonders of science. Where are you on the map? Let me know where you are in the world and what time it is in the comments. It's always fascinating to see who's joining us from all around the world, so let's continue. When we ask what the universe is, we are not asking a simple question, you know. We are really asking about everything that has ever existed, everything that exists now, and everything that ever will exist. Well, that is a rather overwhelming thought to begin with. The universe is not just the stars scattered across the night sky or the faint band of the Milky Way stretching above us like a cosmic river. It is the totality of space itself, the fabric in which all distances are measured, and time itself, the quiet river carrying every moment from past to future. And that's the thing. Space and time are not separate stages on which events unfold. They are woven together, inseparable, forming the vast arena we call space-time. Every particle, every flicker of light, every thought in your mind exists within it. You see, when we say the universe contains all matter and energy, we are including things both familiar and profoundly strange. The atoms in your body were forged in ancient stars, scattered into space by colossal explosions, and gathered again through gravity to become planets and people. Energy flows everywhere, sometimes as light warming your skin, sometimes as invisible forces binding galaxies together. Even when we think we see nothing at all, the universe is still there, humming quietly with fields and fluctuations. Emptiness, it turns out, is not truly empty. Perhaps one of the most surprising discoveries of modern science is that the universe is mostly made of vast regions that appear almost completely devoid of matter. Between stars, between galaxies, there are enormous stretches of near-perfect vacuum. If you could drift through these regions, you would find almost nothing to touch, nothing to see. And yet, these cosmic voids are just as much a part of the universe as the brightest star. They shape how galaxies arrange themselves, like bubbles forming in a slowly rising loaf of bread. It is a humbling reminder that the universe is defined as much by absence as by presence, and it is tempting to imagine the universe as a collection of objects floating in empty space. But that picture is deeply misleading. Space itself is not a passive container. It can stretch, bend, and ripple. Gravity, as Einstein taught us, is not simply a force pulling things together. It is the curvature of space-time itself. Massive objects like stars and galaxies change the shape of the universe around them, and everything else responds by following those curves. Time ticks differently near massive bodies than it does far away. Even the passage of seconds is not universal. One of the most astonishing facts, I suppose, is that the universe is expanding, not expanding into something else, not pushing outward from a central point, but expanding everywhere at once. The distances between galaxies are increasing as space itself stretches. If you imagine dots drawn on the surface of a balloon, as the balloon inflates, every dot moves away from every other dot. No dot is the center, and none is special. That is remarkably similar to what is happening on the grandest scale of all. This expansion was discovered not by looking at space directly, but by listening to light. When astronomers observed distant galaxies, they noticed their light was stretched toward redder wavelengths. This redshift told us that those galaxies are moving away from us, carried along by the expansion of space, and the farther away a galaxy is, the faster it recedes. This simple observation changed our understanding of the universe forever. It told us that the cosmos is dynamic, evolving, and alive with motion. Now here is where things become even more intriguing. If the universe is expanding today, then in the past it must have been smaller, denser, and hotter. Wind the cosmic clock backward far enough, and you approach a moment when everything was compressed into an unimaginably small state. But we will come to that story soon. For now, it is enough to sit with the realization that the universe has a history. It is not eternal and unchanging, as once believed, but a story unfolding in time. You might wonder, then, where the universe ends. Does it have an edge, a boundary beyond which there is nothing? Well, that is a perfectly reasonable question, and one that has puzzled humans for centuries. The honest answer is that we do not know. What we can say is that there is a limit to how far we can see. Light travels at a finite speed, and the universe has a finite age. That means there is a horizon beyond which light has not had time to reach us. This observable universe is a sphere centered on us, but that does not mean we are at the center of everything. Any observer, anywhere, would see a similar horizon around themselves. Beyond this observable region, the universe may continue, perhaps infinitely, or it may curve back on itself in ways that challenge our intuition. Space might be finite, yet unbounded, like the surface of a sphere, but in higher dimensions. You could travel forever without ever encountering an edge, yet the total volume could still be limited. These ideas are not science fiction. They arise naturally from the mathematics of space-time, and it is worth pausing here to appreciate just how little we truly know. The part of the universe we can observe is vast beyond comprehension, containing hundreds of billions of galaxies, each with hundreds of billions of stars. And yet this may be only a tiny fraction of the whole. There could be regions of the universe forever beyond our reach, separated from us by the relentless expansion of space. Their light will never arrive here, no matter how long we wait. This realization brings with it a certain quiet humility. Our cosmic horizon defines the limits of our direct knowledge, but not the limits of reality itself. The universe does not owe us visibility or accessibility. It simply exists, governed by laws we are still struggling to understand. When we say the universe includes everything, we must also include the laws themselves, the rules that determine how particles behave, how forces interact, how structures form. These laws appear to be remarkably consistent across the observable universe. Light behaves the same way in distant galaxies as it does here on Earth. Atoms vibrate to the same rhythms everywhere we look. This uniformity is one of the great mysteries of cosmology. Why should the universe be so orderly, so comprehensible? Perhaps that is why studying the universe feels so deeply human. We are small, temporary arrangements of matter, Yet we can uncover patterns written across billions of light years. We can reconstruct the history of the cosmos from faint whispers of radiation and subtle distortions of light. In doing so, we learn not only about the universe, but about ourselves. Our atoms obey the same laws as the stars. Our origins are inseparable from cosmic history. And that's the thing. The universe is not separate from us. We are not observers standing outside it. We are participants within it. When you breathe, when your heart beats, when neurons fire in your brain, these are all physical processes governed by the same principles that shape galaxies and black holes. To understand the universe is, in a very real sense, to understand the deep structure of our own existence. As we come to grips with what the universe is, we are naturally led to ask how it came to be this way. If space itself is expanding, if time has a direction, if matter and energy fill the cosmos in such intricate patterns, then there must have been a beginning to this grand story. A moment when space and time themselves emerged, when the universe took its first breath. And so, gently, inevitably, our curiosity carries us forward, toward the question of origins, toward the moment when the universe was born, and the long journey of cosmic evolution truly began. And so we arrive, almost without noticing, at the most delicate question of all. If the universe is expanding, if it has a history written into the motion of galaxies and the cooling of light, then it must have had a beginning. Not a beginning like the start of a journey along a road, but something far stranger, more profound. Well, you see, when cosmologists speak of the birth of the universe, they are not pointing to a place in space. They are pointing to a moment in time. A moment when space itself came into existence. The prevailing idea is what we call the Big Bang. The name is a little unfortunate, I suppose, because it invites the image of an explosion, something detonating at a single point and sending matter flying outward into empty surroundings. But that picture is deeply misleading. The Big Bang was not an explosion in space. It was an expansion of space. There was no center. There was no surrounding void waiting to be filled. Every region of space was once compressed, hot and dense beyond imagination, and then space itself began to stretch. Imagine, if you can, that you rewind the universe like a piece of music played backward. Galaxies draw closer together. The space between stars shrinks. Light becomes hotter and more energetic. Eventually, all the structures we recognize dissolve into a glowing, opaque fog. Keep going, and the distinctions between matter and energy blur. Keep going further still, and the very concepts of distance and duration begin to lose their meaning. And that's the thing. The Big Bang marks not just the beginning of matter, but the beginning of time itself. Before that moment, asking what came before is like asking what lies north of the North Pole. Time, as we understand it, was born with the universe. There was no ticking clock waiting in the dark. There was no empty stage. Time began as the universe began, flowing outward with the expansion of space. This is one of the most unsettling ideas in all of science. Our intuition insists that there must always have been a before, but the equations suggest otherwise. Time has a starting point. In those earliest moments, the universe was unimaginably hot. Temperature is a measure of motion, of how violently particles jostle and collide. At the beginning, everything was packed so tightly that motion was extreme. The universe glowed brighter than any star, filled with energy so intense that ordinary matter could not exist in stable forms. Atoms were impossible. Even protons and neutrons struggled to hold together. The universe was a seething ocean of fundamental particles and radiation, all interacting constantly, all trapped in a cosmic furnace. As the universe expanded, it cooled. Expansion creates room, and room allows energy to spread out. This cooling was not abrupt. It was gradual, relentless, and transformative. With each passing moment, new possibilities emerged. Forces that were once unified began to behave differently. Particles acquired distinct identities. The universe was settling into the rules that still govern it today. One of the most extraordinary aspects of this story is how quickly structure began to form. Within minutes of the beginning, conditions had cooled enough for the first atomic nuclei to assemble. Protons and neutrons combined to form the simplest elements, primarily hydrogen and helium, with trace amounts of others. These were the raw ingredients of everything that would follow. Every star, every planet, every living cell traces its ancestry back to these first few minutes of cosmic history. And, it's worth pausing here because this is not speculation in the casual sense. We have evidence. We see it in the relative abundance of elements throughout the universe. Hydrogen dominates, helium follows, and heavier elements are comparatively rare. This pattern is precisely what the Big Bang predicts. The universe itself carries a memory of its earliest moments written into its chemical makeup. There is another, even more haunting piece of evidence. Long after the universe cooled enough for atoms to form, light was finally able to travel freely through space. Before that, the universe was opaque, like the surface of a star. But once electrons settled into orbits around nuclei, space became transparent. The light released at that moment has been traveling ever since, stretched and cooled by the expansion of the universe, until today it appears as a faint glow in every direction. This cosmic background radiation is the afterglow of creation itself, a whisper from a time when the universe was young. When we detect this radiation, we are not just seeing far away, we are seeing far back in time. We are receiving a message sent billions of years ago, telling us that the universe really was hotter, denser, and smaller in the past. And that's the thing. The universe remembers its own birth, and with the right instruments, we can listen. Of course, there are limits to how far back our understanding can reach. As we approach the very beginning, our current theories begin to break down. Gravity, described so successfully by general relativity and the quantum world, governed by uncertainty and probability, do not yet speak the same language. Near the beginning, both are essential. We are missing a deeper theory that can unite them. And so, there is a veil drawn over the first instant itself. We can describe what happened fractions of a second after the beginning, but the very start remains mysterious. Perhaps that mystery is appropriate. After all, the origin of everything is not a small question. It may be that our current concepts are simply not enough, or perhaps future insights will reveal that the beginning was not quite what we imagine. Some ideas suggest cycles, others suggest multiple universes, others still hint that the beginning we describe is only part of a much larger reality. For now, the Big Bang remains our best, most elegant explanation, grounded in observation and tested by evidence. What is deeply moving, I think, is that this grand cosmic beginning is directly connected to our own existence. The expansion that began then is still happening now. The cooling that allowed atoms to form eventually allowed stars to ignite, galaxies to assemble, and planets to coalesce. Inside stars, the simple elements forged at the beginning were transformed into heavier ones, scattered again by stellar deaths, and reused in new generations of stars and worlds. You are made of material that has been recycled through cosmic history, shaped by processes that began at the birth of the universe. And, when you consider that, the Big Bang stops feeling like an abstract idea. It becomes personal. The fact that the universe began hot and dense explains why there are stars to light the night sky, why there are planets beneath our feet, why chemistry is rich enough for life to exist at all. The beginning set the conditions for complexity, for structure, for meaning. As we follow this story forward, from a hot, uniform beginning toward a universe filled with intricate patterns, another question naturally emerges. If space was born and has been expanding ever since, and if time itself began flowing at that moment, then space and time must be deeply intertwined. To understand the universe properly, we must understand how space and time shape each other, how motion and gravity affect the passage of moments, and how the universe we inhabit is not just a place, but a dynamic fabric through which we are constantly moving. And so, gently, inevitably, Our journey carries us onward into the strange and beautiful relationship between space and time itself. And so, having followed the universe from its hot and brilliant beginning, we find ourselves asking a quieter but far stranger question. What exactly are space and time, now that we know they were born together? You see, for most of human history, space was thought of as a passive stage, an empty container where events simply happened, and time was imagined as a universal clock, ticking away at the same steady rate for everyone, everywhere. It felt comforting, predictable, but the universe, as it so often does, had other ideas. Modern physics tells us that space and time are not separate things at all. They are woven together into a single fabric we call space-time. And that's the thing. You cannot change one without affecting the other. Distance and duration are linked in ways that defy everyday intuition. To move through space is also, in a sense, to move through time. We are all traveling through space-time constantly, even when we feel perfectly still. This idea emerged when scientists began to notice something unsettling. The laws of physics seemed to demand that the speed of light was the same for everyone, no matter how fast they were moving. That simple statement has profound consequences. If light's speed is fixed, then time itself must be flexible. Seconds stretch, lengths contract. What one observer measures as a moment, another may experience as longer or shorter, depending on motion and gravity. Perhaps the most astonishing consequence is that time does not flow at the same rate everywhere in the universe. Near massive objects, time slows down. Gravity is not just a force pulling things inward. It is the bending of space-time itself. A massive body like a star or a planet creates a depression in space-time, and clocks placed deeper in that depression tick more slowly than those farther away. This is not a metaphor, it has been measured. Time on Earth passes slightly more slowly than time far from any gravitational influence. And this means that time is not absolute. There is no single cosmic clock governing the universe. Each path through space-time has its own rhythm. Your personal experience of time is shaped by your motion and your surroundings. If you were to travel at extreme speeds, close to the speed of light, time for you would slow relative to those you leave behind. When you returned, you would find the universe older than you expected. This is not science fiction. It is a direct consequence of how space-time works. Motion itself changes time. The faster you move through space, the more slowly you move through time. It sounds poetic, almost mystical, but it is simply the geometry of the universe revealing itself. Space and time trade off against each other, like two sides of the same coin. You cannot maximize one without sacrificing the other. This leads us to a profound realization. Time does not pass uniformly across the cosmos. There is no universal now. Events that appear simultaneous to one observer may not be simultaneous to another. The universe does not agree on what is happening at this very moment. Instead, reality is a tapestry of perspectives, each valid within its own frame of reference. I suppose this challenges something very human. We feel time as a steady flow, an arrow pointing from past to future, memories behind us, possibilities ahead. And yet, the laws of physics, at their deepest level, do not strongly prefer a direction. Most equations work just as well forward as backward. So where does the arrow of time come from? The answer seems to lie not in the fundamental laws themselves, but in the condition of the universe at its beginning. The early universe was remarkably ordered. Over time, disorder tends to increase. This tendency is what gives time its direction. Entropy, the measure of disorder, increases as the universe evolves. Cups fall and shatter, but shards do not spontaneously reassemble. Stars burn their fuel and fade, but they do not reignite themselves. Time moves forward because the universe changes from order to disorder. And that's the thing. The arrow of time is written into the history of the cosmos. It is a consequence of how the universe began. Our sense of past and future, of cause and effect, is tied to this gradual increase of entropy. Memory itself depends on it. Without a direction to time, there could be no record of what has been. Yet even as time has a direction, it is not something we can reverse. We can move forward through time effortlessly, one moment after another, but going backward appears impossible. Physics allows us to imagine strange scenarios, but no mechanism has ever been found that permits travel into the past without contradictions. Time seems to permit memory, but not return. This makes time feel both intimate and elusive. It governs our lives completely, yet remains one of the least understood aspects of reality. We feel it passing in our bodies, in aging and change. But on cosmic scales, time behaves in ways that defy intuition. Near black holes, time slows dramatically. At the event horizon, from an outside perspective, time nearly comes to a halt. The universe allows such extremes, quietly, without concern for our comfort. And, when you step back and take it all in, space-time begins to feel less like a background and more like an active participant in the universe. It stretches as the universe expands. It ripples when massive objects move, sending gravitational waves across the cosmos. These waves are distortions in space-time itself, echoes of violent events like merging black holes, traveling vast distances before gently shaking our detectors here on Earth. Space is not empty. Time is not uniform. Together, they form a dynamic, responsive fabric, and we are embedded within it. Every step you take, every thought you think, traces a path through space-time. Your life is a world line, a unique thread woven into the cosmic tapestry. Perhaps that is why the study of space and time feels so deeply philosophical. It forces us to reconsider what we mean by now, by here, by existence itself. The universe is not a static picture. It is a process, a continual unfolding shaped by geometry and motion. As we begin to understand space-time, another layer of complexity emerges. Space-time does not exist on its own. It is shaped by matter and energy, and in turn, it shapes how matter and energy move. This interplay gives rise to structure on the largest scales. Over billions of years, tiny variations in density, amplified by gravity and guided by the curvature of space-time, grew into vast collections of stars. And so, naturally, our attention drifts from the abstract fabric of the universe to the luminous islands it supports. From space-time itself, we are led to the grand cities of stars, swirling and colliding across cosmic time, the galaxies. And so, from the abstract fabric of space-time, our attention drifts naturally toward the places where matter has gathered, where gravity has patiently sculpted structure over billions of years. You see, space-time on its own is subtle, almost invisible to our senses. But when matter begins to clump, when tiny differences in density are amplified over cosmic time, something remarkable appears. Galaxies, vast islands of stars, gas, dust, and dark matter drifting through the expanding universe like luminous cities suspended in the dark. When astronomers first began to truly grasp the scale of the universe, they were stunned to discover just how many galaxies there are. Not dozens, not thousands, but hundreds of billions scattered throughout the observable cosmos. Each one is a system unto itself, bound together by gravity, evolving over immense stretches of time. And that's the thing. When you look up at the night sky and see a few thousand stars at most, you are seeing only the tiniest hint of what is really out there. Beyond our own galaxy lie uncountable others, each glowing faintly across unimaginable distances. Every galaxy contains billions of stars. Some contain even more. These stars are not randomly sprinkled. They move in ordered patterns, orbiting a common center, responding to the collective pull of gravity. Between them lie vast clouds of gas and dust, the raw material for future generations of stars. Galaxies are not static collections. They are dynamic ecosystems, constantly changing, recycling matter, lighting up and fading across cosmic time. And what's particularly beautiful is that galaxies come in many shapes and forms. Some are graceful spirals, their arms winding outward like cosmic pinwheels, glowing with young, blue stars. Others are elliptical, smooth and rounded, filled mostly with older, redder stars, moving in more random orbits. Then there are irregular galaxies, chaotic and asymmetrical, often shaped by gravitational encounters or violent histories. The universe, it seems, has a taste for diversity. Our own home, the Milky Way, is a spiral galaxy. We live embedded within its disk, about halfway between the center and the outer edge. From our vantage point inside it, we see the galaxy as a hazy band of light stretching across the sky, the combined glow of countless stars along the plane of the disk. It took a long time for humans to realize that this Milky Band was not a cloud or a distant structure, but our own galaxy seen from within. I suppose that realization was a humbling moment. We are not looking out at the Milky Way. We are inside it. The Milky Way itself contains hundreds of billions of stars, along with vast amounts of gas and dust. At its center lies a supermassive black hole, millions of times the mass of the Sun, quietly anchoring the galaxy with its immense gravity. It does not dominate the galaxy's motion in a dramatic way, but it plays a crucial role in the dynamics of the central regions. Many galaxies, it turns out, harbor similar giants at their cores. Galaxies are not isolated. Gravity ensures that they interact. Over time, they drift toward one another, pulled together by their mutual attraction. When galaxies meet, they do not collide like solid objects. Stars usually pass by one another without contact, separated by vast distances. But their gravitational fields intertwine, distorting shapes, triggering waves of star formation, and sometimes merging two galaxies into one larger system. These mergers are among the most dramatic events in cosmic history. You see, the universe is hierarchical. Small structures form first, then combine to create larger ones. Early in cosmic history, small proto-galaxies emerged from slight density variations left over from the early universe. Over billions of years, these small systems merged again and again, building up the large galaxies we see today. Our own Milky Way is the product of countless such mergers, its stars carrying subtle chemical fingerprints of ancient, long-absorbed galaxies. And that's the thing. Galaxies remember their past, the motions of stars, their compositions, their distributions, all tell a story. By studying them, astronomers can reconstruct the history of galaxy formation and evolution. They can see evidence of ancient collisions, of periods when star formation surged, of times when galaxies were stripped of gas and left to slowly fade. What's particularly fascinating is that galaxies do not distribute themselves randomly through space. They form vast cosmic structures, filaments and clusters, separated by enormous voids. On the largest scales, the universe resembles a cosmic web, with galaxies tracing out strands of matter shaped by gravity and dark matter. This structure emerged from tiny fluctuations in the early universe, amplified over time by gravitational attraction. Once again, we see how the earliest moments of the cosmos continue to shape what we observe today. Galaxies also evolve internally. Star formation is not constant. Some galaxies are vibrant and active, birthing new stars at a rapid pace. Others are quiet, their gas reservoirs depleted, their stars aging peacefully. Why some galaxies shut down star formation while others remain active is still an area of intense study. Interactions, environment, internal processes, and the influence of central black holes all seem to play a role. And when you think about it, galaxies are the true engines of cosmic creativity. They are where stars are born, where elements are forged, where the conditions for planets and eventually life are established. Without galaxies, the universe would be a far emptier, simpler place. It is within these vast structures that complexity takes root. The Milky Way, for all its grandeur, is just one among many. Nearby we find the Andromeda Galaxy, another large spiral, slowly drifting toward us. In billions of years, the two will merge, reshaping both galaxies into a new system entirely. This is not a catastrophe in the human sense. By then, Stars will continue their orbits largely unharmed, but the night skies of whatever worlds exist may be dramatically transformed. Perhaps what is most striking about galaxies is how long-lived they are. Individual stars are born and die, but galaxies persist, evolving slowly across billions of years. They are the great archives of cosmic history, preserving within them the record of the universe's past. When we study distant galaxies, we are also looking back in time. Their light has taken so long to reach us that we see them as they were long ago, sometimes when the universe was only a fraction of its current age. And that's the thing. Galaxies are time machines. They allow us to watch the universe grow up. By comparing nearby, mature galaxies with distant young ones, we can trace how structure emerged from simplicity, how order arose from the near uniformity of the early cosmos. As we linger among these grand stellar cities, another realization quietly emerges. Galaxies are vast, but they are built from smaller components. Their light comes from individual stars, each with its own story, its own birth, life, and death. To truly understand galaxies, we must look closer, beyond the swirling arms and glowing cores, and focus on the stars themselves, those brilliant points of light that have guided human curiosity for millennia, and whose lives shape the destiny of galaxies and everything within them. And so our gaze narrows gently, from the vast sweep of galaxies to the individual points of light that give them life. You see, galaxies are luminous because of stars, and stars themselves are the true alchemists of the universe. They are not just lights in the sky. They are engines of creation, places where the simple elements of the early universe are transformed into the rich diversity of matter that makes planets, oceans, and eventually people. Every star begins its life in a cloud, not a cloud like those drifting above us on Earth, but an enormous cold gathering of gas and dust floating quietly between the stars. These clouds can span many light years, their matter spreads so thin that they seem almost empty. And yet, gravity is patient. Over time, tiny variations in density grow. Regions collapse inward, growing denser and warmer. As they shrink, they spin, flattening into disks, fragmenting into smaller clumps. Within these collapsing knots, stars are born. Well, you see, a star is essentially a battle. Gravity pulls inward, trying to crush matter into ever smaller volumes. Heat and pressure push outward, resisting collapse. When the balance is just right, a star ignites. At its core, temperatures climb high enough for nuclear fusion to begin. Hydrogen nuclei merge to form helium, releasing energy in the process. That energy flows outward, and a star begins to shine. Our own sun is one such star. It feels special to us, of course, because it is close, because it warms our world and lights our days. But in the grand scheme of the universe, the sun is remarkably ordinary. It is a medium-sized star, neither particularly massive nor especially small. And that's the thing. The universe does not require extraordinary stars to produce extraordinary outcomes. Even an average star can host planets, chemistry, and perhaps life. Stars come in many varieties. Some are far more massive than the sun, blazing with intense blue light, burning their fuel at a furious pace. Others are small and cool, glowing faintly red, sipping their fuel slowly over trillions of years. A star's mass determines almost everything about its life, its brightness, its color, its temperature, and ultimately, its fate. Massive stars live fast and die young. They burn through their nuclear fuel quickly, sometimes in just a few million years. Their cores fuse heavier and heavier elements, moving beyond hydrogen and helium to carbon, oxygen, silicon, and eventually iron. But iron marks a turning point. Fusing iron does not release energy. When a massive star's core fills with iron, the outward pressure falters. Gravity wins. The core collapses catastrophically, triggering a supernova explosion that can briefly outshine an entire galaxy. And, these explosions are not just dramatic endings, they are acts of creation. In the intense heat and pressure of a supernova, elements heavier than iron are forged. Gold, silver, iodine, and many others are formed in these final moments and scattered into space. The debris enriches surrounding gas clouds, seeding future generations of stars and planets. Without dying stars, the universe would lack many of the elements essential for life. Smaller stars, like the Sun, live much longer lives. They spend billions of years quietly fusing hydrogen into helium, stable and predictable. When their fuel eventually runs low, they swell into red giants, shedding their outer layers into space. Their cores are left behind as dense white dwarfs, slowly cooling over immense spans of time. Even in death, these stars contribute to the cosmic cycle, returning material to the galaxy. Color is one of the most immediate clues a star offers about itself. Blue stars are hot and massive, burning intensely. White and yellow stars, like the Sun, occupy a middle ground. Red stars are cooler and often smaller, though some red giants are enormous in size despite their lower surface temperatures. Color is not just aesthetic. It is a window into a star's physics, revealing how energy flows from its core to its surface. And that's the thing. When you look up at the stars, you are seeing physics made visible. Every hue, every brightness, every subtle flicker tells a story about temperature, composition, and motion. Astronomers decode these stories by splitting starlight into spectra, revealing fingerprints of elements and clues to stellar motion. Through light alone, we can know the nature of objects trillions of kilometers away. Stars are not solitary beings. Many are born in groups, clusters that drift together through space. Some remain loosely bound, others disperse over time. Some stars form in binary systems, orbiting a companion, exchanging mass, influencing each other's evolution. These interactions can produce phenomena far stranger than isolated stars ever could. Novae, pulsars, and X-ray sources often arise from stellar partnerships. Over time, stars shape their surroundings. Their radiation heats nearby gas. Their winds push material outward. Their deaths shock and stir the interstellar medium. Star formation and stellar death are linked in a continuous cycle. Galaxies breathe through this cycle, forming stars, enriching themselves, and slowly changing character. Perhaps what is most humbling is the realization that stars are finite. Even the longest-lived will eventually exhaust their fuel. The night sky is not eternal in its current form. Stars are born, shine, and fade. The universe is not static. It is a process unfolding across unimaginable timescales. And yet within that vastness, stars create moments of stability. Around many of them, disks of leftover material flatten and cool, giving rise to planets. These planetary systems are not rare. They appear to be a natural byproduct of star formation. And so, from clouds of gas come stars, and from stars come worlds. As we stand beneath the night sky, feeling the quiet pull of curiosity, it becomes clear that to understand our own place in the universe, we must look not only at stars in general, but at the particular system that shaped us. One star, average and unremarkable in cosmic terms, surrounded by a family of planets. A system that drifts through the Milky Way, carrying with it the story of how starlight can give rise to life. And so, naturally, our journey carries us onward, from stars themselves to the planetary system we call home. And so, from the quiet brilliance of stars, our attention settles into a more intimate arrangement. A single star, surrounded by a family of worlds, bound together by gravity and motion. You see, the solar system is not an accident, nor is it unique in its basic design. It is the natural outcome of the same processes that give birth to stars everywhere in the galaxy. Long before there were planets, before there was a sun shining steadily in the dark, there was a cloud, a cold, rotating cloud of gas and dust, drifting within the Milky Way, enriched by the ashes of earlier stars. Gravity, once again, did what it always does. It gathered. As the cloud collapsed inward, most of the material fell toward the center, heating up, spinning faster, flattening into a disk. At the heart of this disk, pressure and temperature climbed until nuclear fusion ignited. The sun was born. And that's the thing. The sun did not form alone. Around it, the leftover material in the disk continued to swirl, collide, and clump together, slowly assembling the planets. The solar system formed from a single cloud, and because of that shared origin, its members carry a family resemblance. The planets orbit in roughly the same plane. They move in the same direction. They are all held in place by the sun's gravity, which dominates the system completely. In fact, the sun contains almost all the mass of the solar system. The planets, moons, asteroids, and comets together make up only a tiny fraction. Everything else is quite literally along for the ride. Well, you see, gravity is the quiet architect here. It keeps planets in stable orbits, preventing them from flying off into space or falling straight into the sun. An orbit is not a perfect balance, but a continuous fall that never quite reaches its target. Planets are constantly falling around the sun, curving through space-time along paths set by mass and motion. This delicate dance has persisted for billions of years, a testament to the deep order underlying the cosmos. Closer to the sun, where heat was intense in the early days, only rocky materials could survive. This is why the inner planets are small and dense, worlds of metal and stone. Farther out, where temperatures were lower, lighter elements like hydrogen and helium could be captured in vast quantities. There, giant planets formed, wrapped in thick atmospheres, accompanied by complex systems of moons. The structure of the solar system reflects its thermal history, frozen into place by gravity. And, among these worlds, one occupies a particularly narrow range of conditions. Earth, not too close to the sun, where water would boil away, not too far, where it would freeze solid. Earth lies within what we call the habitable zone, a region where liquid water can exist on the surface. This does not guarantee life, of course, but it makes life possible. And that's the thing. The position of Earth is not mystical, but it is precise. A small shift inward or outward, and our planet might have been very different. Earth's story is deeply tied to the dynamics of the entire system. The gravitational influence of other planets, particularly the giants, helped shape the early solar system. They stirred material, directed impacts, and perhaps even shielded the inner planets from excessive bombardment. The Moon formed from debris after a colossal impact early in Earth's history, stabilized Earth's rotation, and influences the tides, subtly shaping the rhythm of life itself. The solar system is not static. It moves. The sun, carrying its planetary family with it, orbits the center of the Milky Way. We are not standing still in space. We are traveling at enormous speed, tracing a long path around the galaxy, completing one orbit every few 100 million years. And even that motion is not simple. The galaxy itself moves within larger cosmic structures. Motion is layered upon motion, like currents within currents. And that's the thing. When you think of the solar system, it is tempting to imagine a neat diagram, planets circling calmly around a stationary sun. But the reality is far more dynamic. The solar system is a traveling system, a drifting island of matter shaped by forces acting across vast distances and timescales. Asteroids and comets, the leftover debris from planet formation, still roam the system. Some follow stable paths. Others are nudged by gravitational encounters, occasionally crossing planetary orbits. These objects are reminders that the solar system was once a chaotic place, full of collisions and near misses. Even now, it is not entirely settled. Change continues, slowly, patiently. What's remarkable, I suppose, is how much of our existence depends on this delicate gravitational balance. The length of a year, the cycle of seasons, the stability of climate, all are consequences of Earth's orbit. The tilt of our planet's axis gives rise to variation and rhythm, shaping ecosystems and histories. These are not arbitrary features. They are outcomes of cosmic processes. The sun itself is remarkably steady. For billions of years, it has provided a relatively constant output of energy. This stability is rare among stars and crucial for life. Too much variation and complex chemistry struggles to persist. Too little energy, and life never gets started. The sun's moderate mass and long lifespan make it an ideal anchor for a living world. And, when you consider that, the solar system begins to feel less like a random arrangement and more like a finely tuned environment, not tuned by intention, but by natural processes selecting from countless possibilities. Most planetary systems may never host life. Some may host forms utterly unlike anything we know. Earth happens to be one of the rare places where conditions aligned just so. Yet the solar system is only one example among many. Around other stars, astronomers have discovered thousands of planetary systems, some wildly different from our own. Giant planets hugging their stars, worlds with scorching temperatures, systems with tightly packed orbits. The solar system is not a universal template, but one expression of a broader pattern. Still, it is our home. It is the environment in which humanity emerged, curious enough to look outward and reconstruct its own origins. Every element in your body was forged in stars that lived and died before the sun was born. Every breath you take is connected, through chemistry and gravity, to processes that began billions of years ago. As we move through this story, the scale continues to shrink, from galaxies to stars, from stars to planetary systems. And now, naturally, our curiosity pulls us closer still, from the architecture of the solar system to the individual worlds that inhabit it. Planets of stone and gas, moons of ice and fire, each with its own history, each shaped by gravity, heat, and time. Worlds that invite comparison, imagination, and deeper questions about what it means for a place to be alive. And so we move closer still, from the broad architecture of the solar system to the individual worlds themselves. Planets and moons. These are no longer abstract points on a diagram, but places with surfaces, atmospheres, seasons, histories. You see, once we begin to look carefully, it becomes clear that not all planets are made alike. In fact, many of them are nothing like Earth at all. Some planets have solid surfaces you could, in principle, stand on. Worlds of rock and metal, scarred by craters shaped by volcanism, cracked by tectonic stress. Others have no true surface at all. They are vast spheres of gas, their atmospheres growing denser as you descend until pressure and temperature become so extreme that the very idea of a surface loses meaning. And that's the thing. A planet does not have to resemble Earth to be a planet. Our intuition is shaped by familiarity, but the universe is far more inventive. The giant planets of our solar system are made mostly of gas and ice. Hydrogen and helium dominate, mixed with water vapor, methane, and ammonia. These worlds are enormous, dwarfing the rocky planets closer to the sun. Their gravity is intense, their atmospheres deep and dynamic, filled with storms that can last for centuries. Beneath their cloud tops, pressures climb so high that ordinary matter behaves in unfamiliar ways. Hydrogen itself may become metallic, conducting electricity and generating powerful magnetic fields. Closer in, the rocky planets tell a different story. They are smaller, denser, shaped by heat and impact. Some have thick atmospheres, others almost none at all. Some retain heat internally, driving volcanism and tectonic motion. Others have cooled and become geologically quiet. Each planet reflects a balance between mass, distance from the sun, composition, and history. Change any one of these factors and the outcome can be radically different. And, planets rarely exist alone. Many are accompanied by moons, some of which rival planets in size and complexity. Our own moon is unusually large relative to Earth, and its presence has profoundly influenced our planet. It stabilizes Earth's rotation, moderates long-term climate variations, and raises tides that have shaped coastlines and perhaps even the evolution of life. The moon is not just a companion. It is part of Earth's story. Other planets host far more moons. The giant planets, in particular, are surrounded by rich systems of satellites, each with its own character. Some moons are icy, hiding oceans beneath frozen crusts. Others are volcanic, reshaped constantly by internal heat. Some possess thick atmospheres. Some are larger than the smallest planets. And that's the thing. The line between planet and moon is not always as clear as we might like. Moons experience gravity in complex ways. They are pulled by their parent planets, stretched and squeezed as they orbit. This tidal heating can generate internal warmth, keeping subsurface oceans liquid even far from the sun. Energy does not come only from starlight. It can come from gravity itself. This realization has expanded our ideas about where interesting chemistry and perhaps life might exist. Planets and moons interact continuously. Their gravity shapes orbits, locks rotations, raises tides. Many moons keep the same face toward their planet, just as our moon does toward Earth. This tidal locking is a natural outcome of gravitational interaction over long periods. It creates worlds with permanent day and night sides, environments of extreme contrast, and the diversity of planetary surfaces is astonishing. Some worlds are covered in ice, others in rock, some in clouds so thick they hide the surface entirely. There are planets where rain may fall not as water, but as methane, or even metal vapor. The universe seems almost playful in its variations, exploring every combination allowed by physics. Yet amid this diversity, patterns emerge. Gravity shapes everything. Heat drives change. Distance from the sun influences temperature, but internal heat can matter just as much. History matters. Early impacts, atmospheric loss, magnetic fields, all leave lasting marks. A planet is not defined by one property alone, but by the interplay of many factors over time. When we compare these worlds to Earth, we begin to see just how narrow our own circumstances are. Liquid water on the surface, a stable atmosphere, a magnetic field that shields us from harmful radiation, plate tectonics recycling carbon and regulating climate. None of these features is guaranteed. Earth is not the default outcome. It is one of many possible results. And that's the thing. Studying other planets and moons is not about diminishing Earth's importance. It is about understanding it more deeply. By seeing what other worlds are like, we learn what makes our own world special and what features might be essential for life as we know it. Beyond our solar system, the variety grows even larger. Astronomers have discovered planets orbiting other stars with characteristics that defy our expectations. Worlds larger than Jupiter orbiting closer to their stars than Mercury does to the Sun. Rocky planets in tightly packed systems. Planets orbiting dead stars. The solar system is not the standard. It is one example among countless possibilities. And yet, moons remain an especially intriguing piece of the puzzle. They may offer stable environments, protected from extremes, with sources of internal energy. In some cases, they may be better candidates for life than the planets they orbit. This shifts our perspective. Habitability may not belong only to planets. As we imagine standing on these worlds, or floating above their cloud tops, or drifting through their icy subsurface oceans, we are reminded that the universe is filled with places, not destinations we can easily reach, but environments shaped by the same laws that govern our own world. Each one is a natural experiment, exploring what matter and energy can do under different conditions, and the more we learn about planets and moons, the more we encounter extremes, crushing pressures, bitter cold, blistering heat, radiation, darkness, and in these extremes, we begin to think about gravity again, about what happens when matter is compressed beyond ordinary limits, about objects so dense that planets and stars alike are merely their surroundings. Because lurking behind many planetary systems, shaping their histories and their motions, are objects that challenge our understanding entirely. Remnants of massive stars, collapsed beyond anything we have yet discussed. To follow the story of planets and moons to its deeper conclusion, we must turn toward these strange and powerful entities where gravity reigns supreme and space-time itself seems to bend toward silence. And so we arrive at objects that seem to sit at the very edge of understanding. Born from the death of stars, hidden behind horizons of darkness, black holes are perhaps the most extreme expressions of gravity the universe can produce. You see, when we spoke earlier about massive stars living fast and dying young, we left the story at the moment of collapse. But for the most massive stars of all, collapse does not end with a quiet remnant. It continues, relentlessly, until something extraordinary forms. When a giant star exhausts its nuclear fuel, there is no longer any outward pressure to counter gravity. The core collapses inward with astonishing speed. If the mass is great enough, nothing can halt this collapse. Not electron pressure, not neutron pressure. Gravity overwhelms every known force. Matter is crushed to a point where our current understanding of physics begins to fail. A black hole is born. And that's the thing. A black hole is not an object in the usual sense. It is a region of space-time where gravity has become so strong that escape is impossible. Not even light, the fastest thing in the universe, can break free once it passes a certain boundary. This boundary is called the event horizon. Cross it, and the future points inward, inevitably toward the center. This does not mean black holes are cosmic vacuum cleaners, sucking in everything around them. That is a common misunderstanding. Far from the event horizon, a black hole behaves like any other object of the same mass. If the Sun were replaced by a black hole of equal mass, Earth's orbit would remain essentially unchanged. We would continue circling, unaware of the profound difference at the center. Black holes are dangerous only if you venture too close. Near the event horizon, however, space-time becomes deeply warped. Paths that once led outward now curve back inward. Time itself behaves strangely. To a distant observer, an object falling toward a black hole appears to slow down, its light stretching and fading, never quite crossing the horizon. But for the falling object, time passes normally. It crosses the horizon without noticing anything special at that moment. This difference in perspective is not an illusion. It is a fundamental feature of space-time. At the center of a black hole lies what we call a singularity, a place where density becomes infinite and our equations break down. It is not a place we can describe meaningfully with current physics. The singularity is a signpost telling us that our understanding is incomplete. Nature is doing something there that we have not yet learned how to describe. Black holes come in different sizes. Some are formed from individual stars and are only a few times more massive than the Sun. Others are far more dramatic. At the centers of most galaxies, including our own Milky Way, reside supermassive black holes, millions or even billions of times the mass of the Sun. These giants likely formed early in cosmic history and grew by consuming matter and merging with other black holes as galaxies themselves merged. And it is worth pausing to reflect on how strange that is. Entire galaxies, containing hundreds of billions of stars, are anchored by something completely invisible. The motions of stars near galactic centers reveal the presence of these supermassive black holes. We do not see them directly, but we see their influence. Stars whip around empty regions at tremendous speeds, responding to gravity that must come from something compact and massive. When black holes feed, they can become some of the brightest objects in the universe. As gas and dust spiral inward, they form a swirling disk, heating up through friction and releasing enormous amounts of energy before crossing the event horizon. This accretion process can outshine entire galaxies. Jets of energetic particles can be launched from the regions near the black hole, extending far beyond the galaxy itself. Paradoxically, black holes reveal themselves most clearly when they are actively consuming matter. And that's the thing. Black holes are not merely destroyers, they are also architects. Their energy output can regulate star formation, heating and expelling gas, shaping the evolution of galaxies. In this way, black holes and galaxies grow together, influencing each other over billions of years. For a long time, black holes were purely theoretical. Elegant solutions to equations, but with no direct evidence. That has changed. We now detect gravitational waves from merging black holes, ripples in space-time traveling across the universe. These waves carry information about events that occurred billions of years ago, when two black holes spiraled together and became one. By listening to space-time itself, we confirm that these objects truly exist. We have even seen the shadow of a black hole, a dark silhouette against glowing gas, captured by combining telescopes across the Earth. That image is not a photograph in the usual sense. It is a reconstruction, a triumph of patience and precision. Yet it shows us something real, a boundary beyond which light cannot return. And, when you consider all this, black holes stop being monsters and become something more subtle. They are laboratories where gravity, space, and time reveal their deepest secrets. They challenge our intuitions and force us to confront the limits of knowledge. What is perhaps most unsettling is that black holes are not eternal prisons. According to quantum theory, they may slowly lose mass over vast spans of time, emitting faint radiation and eventually evaporating. This process is extraordinarily slow for large black holes, far exceeding the current age of the universe. Yet it suggests that even the darkest objects are not exempt from change. Nothing, it seems, is truly permanent. Black holes sit at the intersection of our two great theories of nature. General relativity describes their gravity with exquisite accuracy. Quantum mechanics hints at deeper processes near their horizons. But the two theories do not yet agree. Black holes expose this tension more clearly than anything else we know. They are signposts pointing toward a future theory, one that unites gravity and the quantum world. And that's the thing. The universe is not only stranger than we imagine, it is stranger than we can currently explain. Black holes embody that truth. They remind us that knowledge is always provisional, always incomplete, always open to revision. As we move away from these extreme objects, carrying their lessons with us, another mystery begins to loom. We have spoken of stars, planets, galaxies, and black holes. All of them are made of matter we can, in principle, observe. And yet, when we measure the motions of galaxies, when we map the structure of the universe, we find that most of its substance is invisible. Something unseen exerts gravity, shapes galaxies, and drives cosmic evolution. To continue the story, we must now turn toward what we cannot see, but know must be there, the hidden majority of the cosmos, quietly guiding everything we have discussed so far. And so we turn toward a presence that cannot be seen, touched, or captured directly, yet without it, the universe as we know it would simply fall apart. After stars and planets, after black holes with their dramatic gravity wells, we encounter something quieter and far more pervasive. Dark matter and dark energy. Names that sound mysterious because, well, they are. They represent our admission that most of the universe is made of something we do not yet understand. You see, when astronomers first began to measure how galaxies move, something felt wrong. Stars at the outer edges of galaxies were orbiting far too quickly. According to everything we knew about gravity, these galaxies should have flown apart. There was not enough visible matter to hold them together. And yet, they remained intact, rotating calmly through cosmic time. And that's the thing. Either our understanding of gravity was incomplete, or there was more matter present than we could see. Careful measurements across many galaxies pointed to the same conclusion. There is additional mass, invisible mass, exerting gravitational pull without emitting light. This unseen component came to be called dark matter. Not dark because it is evil or ominous, but because it does not interact with light in any detectable way. It does not glow. It does not absorb. It simply pulls. Dark matter outweighs ordinary matter by a wide margin. The atoms that make up stars, planets, oceans, and people account for only a small fraction of the total matter in the universe. Most of it is this invisible substance, quietly shaping the cosmos. Galaxies form within vast halos of dark matter, like luminous foam trapped within invisible molds. Without dark matter, galaxies would not have formed as they did. The universe would look very different, perhaps too smooth, too empty for stars and planets to arise at all. And dark matter does not clump in the same way as ordinary matter. It does not collapse into stars or planets. It remains diffuse, spread out, forming large-scale structures that guide the growth of galaxies. When we map the universe on its largest scales, we find filaments and clusters that trace the distribution of dark matter. The visible universe is like frost on a window, revealing the shape of something we cannot directly see. We know dark matter exists because of its gravitational effects. We see it in the rotation of galaxies. We see it in the motions of galaxy clusters. We see it in the way light from distant galaxies is bent as it passes through massive structures, a phenomenon known as gravitational lensing. Light curves around invisible mass, revealing its presence like a shadow cast by something unseen. And yet, despite all this evidence, we do not know what dark matter is made of. It does not appear to be any particle we have yet identified. It does not interact strongly with ordinary matter. It passes through us constantly if it exists in the way we think, leaving no trace. Entire galaxies are embedded in it, and still it remains elusive. Dark matter, however, is only part of the story. As astronomers began to measure the expansion of the universe more precisely, another surprise emerged. Not only is the universe expanding, it is doing so at an accelerating rate. Galaxies are not merely drifting apart. They are being pushed away from one another faster and faster over time. And that's the thing. Gravity, as we understand it, should slow expansion down. Something else must be at work. This mysterious influence was given the name dark energy. Again, not because it is sinister, but because its nature is unknown. Dark energy appears to act as a kind of pressure inherent to space itself, driving the expansion of the universe to accelerate. It does not clump. It does not form structures. It becomes more dominant as the universe grows larger and emptier. Today, dark energy appears to make up most of the total energy content of the universe. Ordinary matter and dark matter combined are vastly outnumbered. We live in a universe where the majority of its substance is something we do not understand, something that reveals itself only through its large-scale effects. And this realization is deeply humbling. Everything we have discussed so far, stars, planets, galaxies, black holes, all of it belongs to a minority component of the cosmos. The visible universe is the exception, not the rule. The dominant players are invisible. Dark energy is especially strange because it seems to be a property of space itself. As space expands, more dark energy appears, driving even faster expansion. This feedback loop suggests that empty space is not truly empty. It has energy, it has structure, it has consequences. The vacuum is not nothing, it is something, and something powerful. This has profound implications for the future of the universe. If dark energy continues to dominate, galaxies will drift farther apart, eventually becoming isolated islands in an ever-darkening cosmos. Stars will fade, new star formation will slow, the universe will grow colder and more dilute over time. The long-term fate of everything may be shaped by this invisible force. And yet, like dark matter, dark energy remains poorly understood. Is it truly constant, an unchanging property of space, or does it evolve over time? Is it a new field, a modification of gravity, or something even stranger? These questions sit at the frontier of modern physics. What is remarkable, I suppose, is that we can know so much about something we cannot see. Through careful observation, through patterns and motions, we infer the existence of entire components of reality. Science becomes an act of listening rather than seeing, of reconstructing hidden causes from visible effects. Dark matter and dark energy remind us that the universe is under no obligation to be simple or intuitive. Our senses evolved to navigate a small, warm planet, not to grasp the structure of space-time on cosmic scales. And yet, with patience and creativity, we push outward, extending our understanding far beyond what feels natural. And that's the thing. Mystery is not a failure of science. It is its engine. Every unanswered question invites deeper inquiry. Dark matter and dark energy are not embarrassments. They are invitations. They tell us that there is more to learn, that reality is richer than our current theories can capture. As we contemplate a universe dominated by invisible components, another thought begins to surface. Amid all this darkness, amid forces that shape galaxies and expansion, there exist small pockets of complexity, places where chemistry becomes intricate, where energy flows in delicate balance, where matter organizes itself into structures that can observe, question, and wonder. Against overwhelming odds, the universe has produced at least one place where it can reflect on itself, a small world orbiting an ordinary star in a galaxy among billions. And so, having explored the unseen scaffolding of the cosmos, our attention naturally turns toward the most extraordinary phenomenon of all, not dark matter, not dark energy, but life. And so, after wandering through invisible matter and unseen energy, we find ourselves drawn toward the most delicate and astonishing phenomenon the universe has produced so far: life. You see, amid a cosmos dominated by darkness, expansion, and vast empty spaces, there exists at least one small world where matter has learned to organize itself, to copy itself, and eventually to wonder about its own origins. As far as we can tell, Earth is the only place where life has been confirmed to exist. That simple statement carries an enormous weight. Out of hundreds of billions of galaxies, each with billions of stars and potentially even more planets, we know of exactly one world where chemistry crossed the threshold into biology. And that's the thing. This does not mean life is rare, but it does remind us how precious and fragile it may be. Life on Earth began remarkably early in the planet's history. As soon as conditions allowed liquid water to persist on the surface, complex molecules began to assemble. Over time, through processes still being studied, these molecules formed systems capable of metabolism and reproduction. Life did not appear suddenly as a finished product. It emerged gradually, shaped by the environment, responding to energy flows and chemical opportunities. What defines life is not a single molecule or structure, but a pattern, a way of using energy to maintain order, to resist entropy locally while increasing it globally. Living systems are not exceptions to the laws of physics. They are expressions of them. And that's the thing. Life is what happens when the universe explores complexity deeply enough. Earth occupies a narrow range of conditions that allow this complexity to flourish. Its distance from the sun permits liquid water to exist on the surface. Its atmosphere provides pressure and protection. Its magnetic field shields it from harmful radiation. Its internal heat drives geological cycles that recycle nutrients and regulate climate. None of these features is guaranteed. Together, they create a window of habitability. This idea has led scientists to search for other planets in similar regions around their stars. The habitable zone is not a promise of life, but a possibility. It marks where temperatures could allow water to remain liquid, given the right atmospheric conditions. Many planets have been discovered in these zones, worlds larger and smaller than Earth, orbiting stars both similar and very different from our Sun. And, the existence of these planets changes the conversation entirely. It tells us that Earth is not alone in its basic circumstances. The universe seems capable of producing habitable environments in many places. Whether those environments actually host life remains an open question. Life itself may not require Earth-like conditions in every detail. On our own planet, life thrives in extreme environments. Deep beneath the ocean, near volcanic vents, organisms draw energy not from sunlight, but from chemical gradients. In frozen regions, in acidic lakes, in high radiation zones, life finds ways to persist. This suggests that life may be more adaptable than we once imagined. And that's the thing. If life can exist under such a wide range of conditions on Earth, perhaps it can do so elsewhere as well. It may not look like us, it may not rely on the same chemistry, but it could still be alive, processing energy, maintaining structure, responding to its environment. Water, however, appears to play a special role. It is an excellent solvent. It facilitates complex chemistry. It remains liquid over a relatively wide range of temperatures. On Earth, All known life depends on water in some form. This is why the search for life often begins with the search for water, whether on planetary surfaces, beneath icy crusts, or within thick atmospheres. In our own solar system, several moons harbor subsurface oceans. These oceans are kept liquid not by sunlight, but by tidal heating. Gravity provides the energy. These environments are stable over long periods, shielded from radiation, rich in chemical potential. They may not host life, but they demonstrate that habitable conditions can exist far from a star. Beyond our solar system, astronomers analyze the light passing through exoplanet atmospheres, searching for chemical signatures. Certain combinations of gases may indicate biological activity. This is a subtle and challenging task. Non-biological processes can mimic some of these signals. Interpreting them requires caution, humility, and patience. And, despite decades of searching, we have not yet found clear evidence of life beyond Earth. No confirmed signals, no unambiguous biosignatures. This silence has inspired both wonder and unease. Is life rare, or is it simply difficult to detect? Or are we looking in the wrong way? The absence of evidence is not evidence of absence. The universe is vast, and our searches have only just begun. We have examined a tiny fraction of possible worlds, with limited tools, over a brief span of time. Expecting quick answers may reflect more about human impatience than cosmic reality. What is certain is that life, once it emerges, can transform a planet. Earth's atmosphere bears the signature of biology. Oxygen, a reactive gas, persists only because life continually replenishes it. The surface of the planet has been reshaped by living processes. Even the rocks carry traces of ancient organisms. Life leaves fingerprints. And that's the thing. A living planet is different from a dead one in subtle but detectable ways. Given time and technology, it may be possible to recognize those differences across interstellar distances. Yet, life is not just about chemistry and physics. It is also about time. It requires stability over long periods. Sudden changes can wipe out complexity before it has a chance to evolve. Earth has experienced mass extinctions, but it has also enjoyed long stretches of relative calm. This balance between disruption and stability may be crucial. Intelligence adds another layer entirely. On Earth, complex life existed for hundreds of millions of years before a species arose capable of reflecting on the universe. Intelligence is not an inevitable outcome. It is one path among many. Whether it is common or rare remains unknown. And when we look up at the night sky and wonder if we are alone, we are really asking two questions. Is life common? And is intelligence common? The answers may be different. The universe could be filled with simple life, while intelligent civilizations are rare and fleeting. The search for life beyond Earth is not only about finding others. It is about understanding ourselves. By asking where life can exist, we learn what life is. By exploring other worlds, we refine our understanding of Earth's uniqueness and fragility. And that's the thing. Life connects the cosmic to the personal. It links the physics of stars to the chemistry of cells, the expansion of the universe to the beating of a heart. We are not separate from the cosmos. We are one of its expressions. As we stand at this point in the journey, contemplating life in a universe shaped largely by forces we barely understand, another question naturally arises. If life is rare, if distances are vast, if time is limited, what are the prospects for contact, for exploration, for travel beyond our own small neighborhood? The desire to reach outward, to cross the dark between stars, is deeply human. It is an extension of the same curiosity that led us to look up in the first place. And so, having considered life itself, our thoughts now turn toward movement, toward journeys, toward the possibility and the challenge of traveling through the immense spaces that separate one world from another. And so, having contemplated life scattered like rare sparks across an immense and mostly silent cosmos, our thoughts naturally turn toward movement, toward the ancient and persistent desire to leave the familiar ground beneath our feet and venture outward. You see, the story of space travel is not really about machines or rockets. It is about distance, about scale, about the quiet realization that the universe is far larger than anything the human body was ever meant to cross. For all of our dreaming, all of our imagination, there is one simple truth that shapes every journey beyond Earth. Space is vast, almost incomprehensibly so. Even within our own solar system, distances stretch the limits of intuition. Light, the fastest thing there is, takes minutes to reach the outer planets. Spacecraft take years. And yet, this is still our immediate neighborhood, a small clearing in a much larger cosmic forest. Humans have managed, just once so far, to step beyond Earth and set foot on another world. The Moon, a nearby companion, close enough to feel familiar, yet distant enough to feel utterly alien. When astronauts walked on its surface, they carried with them the accumulated curiosity of an entire species. That moment was not just a technical achievement. It was a statement. That matter, organized into life, could look back at its home planet from another world. And that achievement is sometimes underestimated. Leaving Earth is extraordinarily difficult. Gravity binds us tightly. Our atmosphere thins rapidly with height. Space is hostile to biology in nearly every way. Vacuum, radiation, extreme temperatures all conspire against life. To survive even briefly beyond Earth requires careful engineering and constant support. Beyond the Moon, however, the challenges multiply. Mars, often imagined as our next destination, lies at a distance that varies dramatically depending on orbital positions. Even at its closest, it is far enough away that communication is delayed, resupply is impossible, and rescue is out of the question. A journey there is not a trip. It is an expedition into isolation. And that's the thing. Space travel is constrained not only by distance, but by time. Our bodies evolved under specific conditions. Extended exposure to microgravity weakens bones and muscles. Radiation damages cells and increases cancer risk. Long-duration missions test both physiology and psychology. Space does not forgive easily. When we turn our gaze beyond the solar system, the scale becomes even more sobering. The nearest stars are so far away that even light takes years to reach them. With current technology, a spacecraft would require tens of thousands of years to make the journey. Entire civilizations could rise and fall in the time it takes to cross the gulf between stars. This is why interstellar travel, as things stand, is not feasible. Not because of a lack of imagination, but because of fundamental physical limits. Energy requirements grow enormous. Shielding becomes impractical. Lifespans are finite. And above all, there is the speed limit imposed by the universe itself. Nothing with mass can reach or exceed the speed of light. And, this limit is not arbitrary. It is woven into the structure of space-time. The faster you move through space, the more time slows down for you. Approaching the speed of light requires infinite energy. The universe seems to be telling us, gently but firmly, that some distances are not meant to be crossed easily. This does not mean exploration stops. It changes shape. Instead of sending people, we send machines. Robotic explorers travel where humans cannot, enduring cold, radiation, and silence. They carry our instruments, our questions, our curiosity. Through them, we extend our senses across the solar system and beyond. Signals, rather than bodies, become our primary travelers. Light and radio waves cross vast distances with ease, carrying information rather than matter. Through telescopes, we study planets around other stars. We analyze their atmospheres. We measure their temperatures. We listen for patterns that might suggest technology. In this way, we explore without moving. And that's the thing. Exploration is not defined by footsteps alone. It is defined by understanding, by expanding the sphere of what we know. Even without leaving our planet, we have learned the age of the universe, the life cycles of stars, the structure of galaxies. Knowledge travels faster than any spacecraft. Still, The dream of reaching the stars persists. It is deeply rooted in human nature. We imagine generation ships carrying communities across millennia. We imagine cryogenic sleep, waiting out the long darkness. We imagine new forms of propulsion, tapping energies we barely understand. These ideas are not foolish. They are expressions of hope, but they remain speculative. What is more certain is that the universe is not arranged for convenience. Distances are real. Time matters. Resources are finite. Any future expansion beyond our solar system would require not just technology, but patience, cooperation, and a willingness to think on timescales far beyond individual lives. And perhaps there is a deeper lesson here. The difficulty of travel reminds us of the value of where we already are. Earth is not just a starting point, it is an oasis, a rare, fragile place that supports life in a universe that is otherwise largely indifferent. The more we learn about space, the more precious our home becomes. The moon landing did not diminish Earth. It made it visible, a small blue world suspended in darkness. Everything we have ever loved, every story, every species, contained within a thin shell of air and water. Space travel showed us not only what is out there, but what we must protect here. As technology advances, we may venture farther. We may establish outposts on other worlds. We may learn to live away from Earth for extended periods. But even then, the stars will remain distant. The universe will remain vast. The night sky will remain mostly unreachable. And that's the thing. Our limitations are not failures. They are part of the story. They shape how we explore, how we imagine, how we value time and place. The universe invites curiosity, but it does not rush us. As we consider journeys through space, another thought quietly emerges. Travel is not only about distance, but about destiny, about where the universe itself is going. Even if we could cross the stars, what kind of universe would we arrive in? One growing colder, larger, darker, shaped by expansion that never pauses. And so, having followed life and movement as far as they can reasonably go, our attention drifts once more to the grandest scale of all, the future of the cosmos itself, the long arc of time ahead, the question not of where we can go, but of what the universe is becoming. And so we find ourselves looking not outward in space, but forward in time. After stars and galaxies, after life and journeys that stretch the limits of imagination, there remains one final question that quietly hums beneath everything we have discussed. What happens next? What becomes of a universe that has been expanding since its birth, shaped by forces both visible and unseen? Well, you see, the future of the universe is written not in prophecy, but in physics. And yet, even with our best equations, the ending of the cosmic story remains uncertain. What we can say with some confidence is that the universe is still expanding, and not only expanding, but accelerating. Space itself is stretching, carrying galaxies farther apart with every passing moment. If this expansion continues indefinitely, the universe will grow ever larger and emptier. Galaxies beyond our local group will drift so far away that their light will never reach us. Over immense spans of time, the night sky will change. Distant galaxies will fade from view, leaving only our immediate cosmic neighborhood visible. To any observers far in the future, the universe may appear far smaller and quieter than it does to us now. And that's the thing. The universe is not only changing in structure, but in temperature. As it expands, it cools. The intense heat of the early universe has long since faded into a faint background glow. Over time, even that glow will weaken. The universe will continue its slow slide toward lower energy states, toward colder and more diffuse conditions. Stars, the brilliant engines of light and warmth, are not eternal. Each one burns a finite supply of fuel. As time passes, the most massive stars disappear first, ending their lives in spectacular explosions or quiet collapses. Smaller stars persist longer, but even they eventually fade. Star formation will slow as galaxies run out of the cold gas needed to form new stars. The cosmic era of starlight will come to an end. And, this is not something that happens quickly. These changes unfold over timescales that dwarf human history. Civilizations rise and fall in the blink of a cosmic eye. Even entire species occupy only brief moments. The universe, by contrast, is patient. Its transformations are slow, deliberate, almost imperceptible from within. A single lifetime. As stars die, they leave behind remnants. White dwarfs, neutron stars, black holes. Over immense periods of time, even these remnants change. White dwarfs cool and fade into darkness. Neutron stars slow their rotation. Black holes, once thought to be eternal, may slowly lose mass through faint radiation, eventually evaporating after time so vast they defy ordinary language. And that's the thing. Nothing appears to be truly permanent. Even the most extreme objects are subject to time. The universe is a story of transformation, not preservation. If dark energy continues to dominate the expansion of space, then the universe will approach a state sometimes called heat death. Not a dramatic explosion or collapse, but a gradual fading. Energy differences will even out. Useful energy will become scarce. Complexity will be harder to sustain. The universe will approach a cold, dark, and dilute condition where little happens. Yet this is only one possible future. Our understanding of dark energy is incomplete. It may change over time. If its strength increases, expansion could accelerate to the point where galaxies, stars, and even atoms are eventually torn apart. If it weakens or reverses, expansion could slow or stop, potentially leading to a very different fate. Some theories imagine a universe that collapses back in on itself, a kind of cosmic return. Others suggest cycles of expansion and contraction, with each universe giving rise to another. Still others propose that our universe is just one region within a much larger reality, where many universes exist, each with its own laws and histories. And, the honest answer is that we do not know which, if any, of these possibilities is correct. The data we have allows us to peer only a limited distance into the future. Beyond that, uncertainty reigns. But uncertainty is not ignorance. It is an invitation. What is striking, I suppose, is that the universe does not appear to be designed for endings that feel meaningful in a human sense. There is no grand finale, no cosmic curtain call. Instead, there is gradual change, slow transformation, quiet fading. The universe does not rush toward conclusion. It simply continues. This perspective can feel unsettling. We are creatures who seek narratives, beginnings and endings that make sense emotionally. But the universe operates on scales where meaning is not imposed, but discovered. Meaning arises locally, temporarily, in pockets of complexity like life. And that's the thing. Even if the universe grows cold and dark in the far future, that does not diminish what exists now. The fact that stars shine at all, that life arose at least once, that consciousness can reflect on the cosmos, is remarkable regardless of how the story ends. In a universe that may one day be empty, the present becomes precious. The era of stars, planets, and life is not guaranteed forever. We live during a brief window when the universe is rich enough for complexity, warm enough for chemistry, structured enough for curiosity. Perhaps that is the deepest lesson of cosmology. Not despair at an inevitable fading, but appreciation of a fleeting abundance. We are not latecomers to a dying universe. We are early witnesses in a long unfolding. And when we think about the future of the cosmos, we are also thinking about responsibility. If life is rare, powering through the dark, then preserving it matters. If intelligence is fragile, then understanding ourselves becomes urgent. The universe will continue with or without us, but what we do with our moment is up to us. The future of the universe may be uncertain, but its past has already given us something extraordinary. a place to stand, a sky to question, a mind capable of wonder. And as we look ahead into the deep future, beyond stars and galaxies, beyond light itself, we are reminded of something quietly profound. The universe does not need to last forever to be meaningful. It only needs to exist long enough for it to know itself, even briefly, through us. And so, having traced the arc of the universe from its fiery beginning toward a future that stretches into cold and silence, we arrive at a quieter, more intimate frontier. Not a new place in space and not a new era in time, but a deeper way of looking. Because once we ask what the universe will become, it is almost impossible not to ask what it means that it became aware of itself at all. You see, the universe did not have to produce observers. For billions of years, it existed without eyes to see it, without minds to question it. Galaxies formed, stars lived and died, black holes grew and merged, all without commentary. And then, on at least one small planet, chemistry crossed a threshold. Matter began to sense, to remember, to anticipate. The universe, through life, began to look back at itself. And that's the thing. Consciousness is not something separate from the cosmos. It is something the cosmos does. Just as stars shine and galaxies spin, brains think, neurons fire, thoughts arise. The same laws that govern gravity and electromagnetism also govern perception, emotion, and curiosity. There is no sharp boundary where physics ends and meaning begins. Meaning emerges from physics, slowly, subtly, like a melody emerging from vibration. When you look at the night sky and feel wonder, that feeling is a physical process. Atoms in your eyes absorb photons that began their journey millions or billions of years ago. Electrical signals travel through neural networks shaped by evolution. Memories, emotions, questions, all arise from that interaction. The universe is not just being observed. It is participating in the observation. I suppose this reframes our place in the cosmos. We are not outsiders peering in. We are internal processes, temporary patterns of matter and energy that carry within them a record of cosmic history. Every atom in your body has passed through stars. Every heavier element was forged in stellar cores or explosive deaths. Your bones contain calcium made in ancient suns. Your blood contains iron born in violence and scattered into space long before Earth existed. And when you consider that, identity becomes less rigid. You are not merely a person living on a planet. You are a continuation of cosmic evolution. The universe did not stop creating when the stars formed. It continued through chemistry, through biology, through culture, through thought. This leads us to a delicate idea. That intelligence, wherever it arises, may not be an accident, but a natural extension of complexity. Given enough time, enough energy flow, enough stability, matter explores richer arrangements, from particles to atoms, from atoms to molecules, from molecules to cells, from cells to minds. Each step improbable, yes, but not arbitrary. And that's the thing. The universe does not aim for intelligence, but it allows it. It opens doors rather than setting destinations. In some regions, those doors may never be crossed. In others, they may open briefly and then close again. Intelligence may be rare, fragile, temporary, but its very existence tells us something profound about what the universe permits. If there are other intelligences out there, scattered across distant galaxies, they too would be local expressions of the same cosmic rules, different histories, different chemistries, different senses, but all bound by the same space-time, the same limits of light and energy. They would look out at their own skies and ask similar questions. Where did this all come from? Where is it going? And what does it mean that we are here to ask? And even if we never meet them, even if the universe remains silent forever, the question itself still matters. Because meaning does not require an audience. It requires experience. A single conscious moment is already something extraordinary in a universe that could have remained forever dark and unaware. As the universe expands and cools, as stars fade and galaxies drift apart, consciousness may become rarer. The conditions that allow complexity are not guaranteed indefinitely. There may come a time when the universe is too cold, too empty, too uniform to support thinking matter. If that happens, then awareness will have been a brief phase in cosmic history, a flash of reflection between long eras of silence. But brief does not mean insignificant. A spark does not need to last forever to light the dark. And that's the thing. Duration is not the same as value. A thought that exists for a moment can still change everything within its reach. This perspective changes how we think about progress. Progress is not guaranteed. Knowledge can be lost. Civilizations can collapse. Entire species can vanish. The universe does not preserve meaning for us. Meaning must be carried, remembered, renewed. Every generation inherits not only matter, but stories, questions, insights. In that sense, culture is another cosmic process, one that operates on shorter timescales, but with remarkable power. And when we think about the future, we often imagine technologies, machines, expansions. But perhaps the deeper future is about understanding, about learning how to live within limits, how to sustain complexity without destroying its foundations, how to be good ancestors in a universe where time stretches far beyond individual lives. Because if intelligence is rare, then its survival matters, not for the universe, which will continue regardless, but for the universe knowing itself. Awareness is the means by which the cosmos becomes more than motion and energy. It becomes story. And that's the thing. Science itself is part of this story. It is the method by which the universe studies its own behavior. Equations are not external truths imposed on reality. They are patterns we have discovered because reality allows them to be discovered. When we write down a law of nature, we are not commanding the universe. We are listening to it. This listening has limits. There are questions we may never answer. What existed before the beginning, if that question even makes sense? Why the laws have the form they do? Whether reality could have been otherwise? These may lie beyond testability, but not knowing is not failure. It is humility. Perhaps the deepest insight cosmology offers is not certainty, but perspective. It loosens the grip of the immediate. It reminds us that our problems, our fears, our ambitions unfold within a much larger context. That context does not erase meaning. It refines it. When you feel small in the universe, that feeling can be unsettling. But it can also be liberating. Small things can still be precious. Rare things often are. A single living world in a vast galaxy. A single conscious species in a long cosmic timeline. These are not reasons for despair. They are reasons for care. And as we continue to explore, to observe, to think, the universe continues its quiet work. Space expands. Time flows. Stars burn and fade. And somewhere for now, minds are awake, asking questions, telling stories, trying to understand. What comes next is not written, not for the universe, not for us. The future remains open, shaped by laws, yes, but also by chance, by choice, by fragile chains of cause and effect. And so, rather than ending, the story simply leans forward, from understanding toward responsibility, from curiosity toward wisdom, from knowing where we are toward deciding how we will be, because the universe has given us a rare gift, a moment of clarity within vastness, a chance to listen, to learn, and perhaps to choose what kind of chapter comes next. And so we come gently to the end of this long journey, though the universe itself, of course, does not end here. It simply continues, quietly, patiently, as it always has. What changes is not the cosmos, but us. Because after walking from the birth of space and time, through stars and galaxies, through life and thought, something subtle has happened. Our sense of place has shifted. You see, the universe no longer feels like a distant stage upon which our lives briefly flicker. It feels closer now, more intimate, less like an empty void and more like a vast, unfolding story in which we play a small but meaningful role. And that's the thing. Meaning does not require centrality. We do not need to be at the center of the universe for our existence to matter. For a long time, humanity believed it occupied a privileged position, the center of creation, the focus of cosmic intention. Science gently dismantled that idea, not to diminish us, but to place us within a richer and more honest picture. We are not the purpose of the universe, but we are one of its outcomes, and outcomes can still be precious. When you step back and consider the scale of everything we have explored, it can feel overwhelming. Billions of galaxies, trillions of stars, distances so vast that even light struggles to cross them. Timescales so long that human history becomes a thin whisper. It is easy, in the face of such immensity, to feel insignificant. But that reaction misses something essential. Insignificance is not measured by size. It is measured by impact, by experience, by awareness. A single thought, fleeting and fragile, is still something the universe did not have before it arose. Consciousness, even briefly, changes the character of reality. It introduces reflection into a cosmos that could otherwise remain forever unobserved. And this is where science quietly becomes philosophical. Because when the universe produces beings capable of understanding it, a strange loop forms. The cosmos investigates itself. Not perfectly, not completely, but sincerely. Equations, telescopes, theories, all are tools the universe has assembled within itself to explore its own behavior. This does not make us masters of reality. It makes us participants, listeners, translators of patterns into meaning. And that's the thing. Knowledge is not domination. It is relationship. The more we learn about the universe, the more we see how deeply we are woven into it. Every fact we have explored points back to this connection. The atoms in our bodies were forged in stars. The chemistry of life depends on cosmic history. The flow of time we experience is shaped by the geometry of space-time. Even our limitations, our inability to travel freely among the stars, are consequences of the same laws that allow stars to shine and galaxies to form. Science has shown us that the universe is not built for comfort, but it is built for coherence. Its laws are consistent. Its patterns repeat across vast distances. This consistency allows understanding, and understanding, in turn, allows humility. Because the more we learn, the more we realize how much remains unknown. Dark matter and dark energy dominate the cosmos, yet remain mysterious. The origin of the laws themselves is unclear. The ultimate fate of the universe is still uncertain. These are not failures. They are frontiers. And that's the thing. Frontiers are not barriers. They are invitations. They remind us that curiosity is never exhausted, that knowledge is always provisional, that certainty is not the goal. Insight is. In this sense, the journey through the universe mirrors the human experience itself. We begin in ignorance. We learn. We revise. We adapt. We grow older, wiser, more aware of complexity. We realize that simple answers rarely survive close inspection. And yet, this does not lead to despair. It leads to depth. The universe is not simple. It is layered, subtle, occasionally brutal, often beautiful. And it does not care about us in the way a person cares. But it allows us. It permits conditions in which life can arise. It tolerates complexity long enough for it to reflect on itself. That allowance is extraordinary. And, perhaps this is why cosmology resonates so deeply. It speaks to something ancient in us, the same impulse that led our ancestors to map the stars, to tell stories about the sky, to wonder where everything came from. Modern science did not erase that impulse. It refined it, gave it tools, extended its reach. When we say the universe is vast, we are not just making a measurement. We are acknowledging that our everyday concerns unfold within a context far larger than we normally perceive. This can be comforting. It can also be grounding. Problems that feel overwhelming can look different when set against cosmic time. But there is another side to this perspective. If life is rare, if intelligence is fragile, then responsibility follows naturally. The universe does not guarantee meaning, it allows it. And what we do with that allowance matters. Earth is not just our home. It is, as far as we know, a rare oasis of life in a largely lifeless expanse. The thin layer of atmosphere that protects us, the stable climate that nurtures ecosystems, the biodiversity that sustains resilience, all are products of delicate balances that can be disrupted. And that's the thing. Understanding the universe does not pull us away from human concerns. It brings us back to them with greater clarity. It reminds us that caring for life is not parochial. It is cosmic. Our technologies grow more powerful. Our ability to alter our environment increases. With that power comes choice. The universe does not tell us what to value. It shows us what is possible. Meaning emerges from decisions, not from equations. In the far future, stars will fade. Galaxies will drift apart. The universe will grow quieter. Whether intelligence survives long enough to witness those eras is unknown. But right now, in this brief window, awareness exists, curiosity exists, compassion exists, and that may be enough, because the universe does not ask us to solve it completely. It asks us to pay attention, to notice patterns, to respect complexity, to recognize that we are temporary but not trivial. When you look up at the night sky after hearing these stories, it may look the same as it always has. Points of light, darkness between them, but perhaps it will feel different. Each star a fusion engine, each galaxy a city of suns, each empty space alive with unseen structure, and you, standing beneath it all, are not separate from that picture. You are part of it. A local expression of a universe that has spent billions of years becoming able to ask questions. The journey through these facts is not about memorization. It is about orientation, about knowing where you are in the grandest sense, not just on a map, but in time, in history, in the unfolding of reality itself. And so, if there is a final thought to carry with you, perhaps it is this. The universe is vast, but it is not empty of meaning. Meaning arises wherever there is awareness, wherever there is care, wherever there is curiosity. We are small, yes, but we are also rare. We are brief, but we are bright. For a moment, the universe is awake, and we are part of that awakening. And that, I suppose, is something worth holding on to.